Okay, let's get started, please. I'm not sure where everybody is, but I guess in some sense it doesn't matter because we're recording the session, so you can always watch it at home. I guess maybe those who aren't here don't feel like they need to ask questions or stuff like that. I don't know. Okay, so remember what we are doing. We are trying to find something like compactness, right? We're trying to find something like compactness for function spaces, right? We would like to have the property that whenever you've got an infinite sequence of functions, there is a convergent subsequence, right? A uniformly convergent subsequence, right? So that's the idea. Right? And what we did last time was we showed conditions under which we could get a pointwise convergent subsequence, right? But like we said last time, that's not really that great, right? Pointwise convergent subsequences, aren't really that useful. What we really would like to have is a uniformly convergent subsequence. So moving from pointwise convergent to conditions which ensure the existence of uniformly convergent subsequences. Okay. So again, this is a kind of compactness result. We're trying to get something that's like compactness. We're basically compactness. Okay, so Rudin gives an example. He gives this question. Suppose you have a uniformly bounded pointwise convergent sequence on a compact set. Right. So the question is, like, does having a uniformly bounded pointwise convergent sequence on a compact set imply that there exists a uniformly convergent subsequence? Right. So again, this is one of these things like, suppose we're on a compact set. Suppose we've got uniform bounds, right? So everything is bounded between two values, right? And further, we have got pointwise convergent. Is that enough to guarantee uniform convergence? And the answer is no. That's not enough. And he gives an example. So I'm just going to write up this example. He gives this example on this compact set. These functions pointwise converge to 0. They're uniformly bounded. Pointwise converge to 0, and they're on the compact set, but they're not uniformly convergent. Okay, so I'll let you read that if you want. It's not much to talk about. So this isn't enough to guarantee to ensure the compactness the sequential compactness that we're looking for. So what turns out to be the key idea is something called equicontinuity. So this is really the necessary concept. Equicontinuity. Okay. So here, let me give the definition. You have f, a collection of functions on some set E into the complex numbers. Okay, so you've got a bunch of complex valued functions. If for all epsilon greater than 0, there exists a delta such that whenever you have 2 points within delta of each other, then the distance between f of x and f of y is less than epsilon for all f in your family. Then we say that f is an equicontinuous family on E. Okay, so let's think about this definition. What does this seem like? Can anyone sort of parse this definition? Like, what does the definition mean to you? Whatever epsilon you're given, there's a delta such that whenever 2 points are close to each other, the distance of the outputs is smaller than epsilon for all f in the family. What does this remind you of? Does this remind you of anything? This is kind of similar to something. Keisha, what do you think?
Continuity.
Continuity, yeah. So continuity, remember, is you've got continuities at some point, right? There's some delta so that around that point you've got this single function, and around that point there's somebody gives you an epsilon. Somebody gives you an epsilon, and you can find a delta so that all the values stay between those bars, right? So yeah, this is like continuity, but it's what else is it like? No. Uniform convergence. Well, I don't know if I'd say uniform convergence, right? Because we're not. Uniform continuity. Yeah, uniform continuity. I'm sure that's what you meant to say. Yeah, because the other makes no sense. Yeah, it's like uniform continuity, right? Because the delta doesn't depend on the x, right? For continuity, the delta depends on the x. For this thing, the delta doesn't depend on the x, right? So it's a kind of uniform continuity, but uniform continuity is just for a single function, right? And here we've got that this delta not only works for every pair of points, but it also works for everybody in the family. Okay, so it's uniform continuity uniformly, right? It's a uniform over the family, uniform continuity. Okay, you can think of this. I think the best way to call this is it's uniform continuity. Yeah, Keisha. Okay, so it's a uniform continuity. Okay. Okay, so for example, right, if I have a family, suppose F is a finite collection, F1 through Fn, a finite collection of uniformly continuous functions. Is it equicontinuous? Suppose you have a finite collection of uniformly continuous functions. Is it then equicontinuous? Don't answer. Think. And then talk. Talk with somebody for a minute or so. Okay, what's the answer? Is it equicontinuous? James?
Yes.
Yes, absolutely. Why? Why is it equicontinuous? Like somebody, so given an epsilon, how do we find the magic delta? The delta that works everywhere and for everybody? Take the maximum delta? Not the maximum. Rather the minimum, right? Because you're going to want the delta that works for everybody, right? So the point is that, right, we know that each of these guys being uniformly continuous is going to have a delta that works, right, for that function only, right? But we want a delta that works for every function in the family. So take the smallest one, right? That smallest one will work for, everybody. Okay. So given this, we know that there exists delta I such that if these guys are within delta I of each other, then the distance of Fix from Fiy is smaller than epsilon, right? Right. So for each function, there's a delta I that works. But then take delta to be the minimum of these guys, right? Then if you're smaller than that minimum, you're smaller than every delta I, right? Smaller than that minimum, you're smaller than every delta I, and so all this is going to be less. This difference is going to be less than epsilon for every function in the family. Okay. So just to give a simple example to clarify the concept. Okay. Okay. So you see what it is, right? It's a uniform continuity, but a kind of uniform continuity. Okay. We're going to give now a condition or conditions implying equicontinuity. Okay. So here's a theorem. Suppose you have a bunch of continuous functions on some metric space K. Okay. If K is compact and 2, the F sub n converge uniformly, then the family is equicontinuous. Okay, and in my notes it says, make them do this. Easy. Okay, so give it a shot. Take a few minutes and see if you can figure out why this ought to be true. Okay, you've got a bunch of continuous functions on a compact set, and continuous functions on a compact set, right? So you know that they're uniformly continuous, right? Everything's uniformly continuous, and they converge uniformly. So why does that guarantee that you can control the continuity, right? That they're uniformly continuous. Okay. I'll give you 3 minutes. 3 minutes. That's not enough, but that's all I'm going to give you. It's enough to get an idea of it.
Should we actually write this down?
sketch out something. So think about, draw some picture, like, okay, right, what does this mean to you? What's your intuition about it, right? You got uniformly continuous functions. You've got uniform convergence. In other words, you've got that tube property, right? What am I going to do? Standing practice. I don't have anything like the tube or anything like that for equicontinuity. So, do you remember?
Like what would differentiate a uniformly continuous function from an equicontinuous function?
There is no equicontinuous function.
Oh yes. Yeah,
It's a family of functions. So yeah, so that's actually the difference right there, right? That it's, you would have a family of uniformly continuous functions, okay, but the delta works consistently throughout. So whatever delta you've chosen works for the whole family. So it's like uniform continuity, but now you're talking about a whole collection of uniformly continuous functions, and where the delta worked at every point in your domain for uniform continuity. Here, it not only does that, but it works. That delta also works for across the whole family. That's why it's equicontinuity. Maybe it'd be better to call it equi-uniformly continuous.
No, it makes sense.
Okay.
I think.
Yeah, but I'm afraid I don't have any picture. Just it's more of a mental concept, this one. Okay, talk to somebody nearby and say, we've got this and this and this and this. This something like this ought to work. Okay. Sorry, I'm going to cut in. Does anybody have
It makes sense. Like, is it epsilon?
does anyone have an idea of how we might prove this? Does anybody have an idea of how we could do this? Or some yeah, Eric.
Can we like break it so that we have like a capital N, such that if N is greater than capital N, then f of f of n is within epsilon over 2 distance from f, the function you're convergent to?
Sure, we could do that. So you could say, well, look, we've got uniform convergence, right? And we're trying to show that these guys are uniformly continuous. I'm sorry, uniformly continuous, right? So let's take an epsilon tube around f here. Okay, so we take the epsilon half tube, say. Actually, we're gonna need the epsilon third tube. Doesn't. Anyway, it'll work out. So yeah, so you know that past a certain time, everybody lies inside this epsilon over 2 tube. Yeah. So then, what would you do? What's your idea?
The piece was the epsilon over 3, but I was thinking like if for those functions, if we have a delta, then I want the delta to be mapped to epsilon over 2 radius, and then I'll have like epsilon over 2 plus epsilon over 2. So I get within for any of the f of n that are past big N, if there's a delta, then I get an epsilon.
Okay.
Or something like that. It's kind of
Yeah. So what you're saying is that all of your functions are going to be close to this f, right? Well, I mean, there's maybe finitely many guys who are outside, right? But so there's finitely many sort of bad guys, right? So bad functions. Okay. But then past a certain, there's only finitely many. The rest of them are inside this tube here, right? And you think, well, f is uniformly continuous, so these guys ought to be uniformly continuous also, right? So we should be able to find a delta that works for f, and that hopefully will work for the other guys as well, right? The guys that are close to it. Okay, so that delta will work for everybody inside the tube. What about the guys outside of the tube?
I don't know if it needs to work, but then since this gives you like a finite set of deltas, you can just pick the minimum of one of the deltas.
Yes, exactly. So yeah, so you would just say, well, there's only finitely many guys out here anyway. Each of them is uniformly continuous, and so we'll take a delta for each one of those, and then take the minimum of that guy's delta and all these deltas, and that'll do it. That's the way. Okay. So yeah, right? Yeah, everybody get that? That's exactly the way you want to be thinking about this sort of problem. Okay. You think, well, look, you know, these guys converge uniformly to f, and f is uniformly continuous. Right? So I can get these guys, you know, basically as close as I desire. There's all these other guys outside, but there's only finitely many, and we just said that if you've got finitely many guys, that's equicontinuous anyway. So let's put that all together. Okay. So here's the proof. Okay. So fix an epsilon. We want a delta so that whenever the distance of x and y is less than delta, we have that the distance of fn x from fn y is less than epsilon for all n. Okay, that's what we desire. Okay. So by uniform convergence, as Eric was just suggesting, we know that there exists an n such that if we're past that point, the distance between f let me check yeah. I'm going to do something a little funny, but such that if you take two things here, then fnx minus fmx is smaller than epsilon over 3. Okay, right. This is so I'm just using the Koshi criterion for uniform convergence. Okay, in particular, if n is bigger than n, I know that the distance of fn from f capital N is less than epsilon over 3. Okay, so I'm taking my m to be that capital N, and I'm letting my n be anything bigger than capital N. Okay. I could do exactly what Eric said and simply take one of these guys to be the f that it converges to. But I'm going to follow the proof in Ruden's book because it's not any better, but it's kind of neater, a little bit neater. Okay. Okay. So okay, so now by our previous remark, f1 to f capital N is equicontinuous. Right, so if we look at these guys from f1 through fn, these are the bad guys. Right? These are the bad guys. So we know, but they're not that bad because there are finitely many of them, and so they're an equicontinuous family. So we know that there exists a delta such that if this is less than delta, then the distance between fi x and fi y is less than epsilon over 3 for I being 1 and capital N. Okay, so now all we have to worry about is the guys who are inside the tube, right? We've got a delta that works for the guys outside the tube. Does this delta work for the guys inside the tube? Okay. And remember, the guys inside the tube are within epsilon 3 of f sub n, which is one member of this family. Okay, right. We're putting the tube around this last guy. Okay. So you say, okay, well, suppose n is bigger than n. Do we still have this property, right? Then if, again, delta xy is less than delta, I'm saying dxy is less than delta, let's think the distance between fnx and fny what am I going to write here? Kesha? Well, not yet. Right. So this is just one of those guys. Exactly. I'm going to use the triangle inequality. So it'll be like, as usual, I'm going to add in some funny-looking zeros. So fnx plus, minus f capital Nx plus f capital Nx minus f capital Ny plus fn capital Ny minus f lowercase ny. Right? So I guess I just throw in these funny looking zeros as usual to get these distances. Right? So I get the distance from f sub n to f sub capital N, which I know is smaller than epsilon over 3. Same thing over here. This is smaller than epsilon over 3. And by the equicontinuity, I know that this thing is smaller than epsilon over 3. So uniform convergence of continuous functions on a compact set forces equicontinuity. Any questions? Right. So the picture you have in your mind here is that here was this f sub n, here was the delta tube around it, right? We already dealt with the guys outside. Now we're looking at the guys inside, right? So you have somebody inside here, and you're wondering about its behavior between x and y that are close together, right? But you know that f sub n behaves well, right? So the distance between f sub n of x and f sub capital N of x and f sub capital N of y is small. And you know that the distance between this and that is small, and the distance between that and that is small, right? So that's less, this vertical distance is epsilon over 3, this vertical distance is epsilon over 3, right? And then this distance between the values of f sub n is less than epsilon over 3 also. Okay. Any questions? Any questions? I don't know if you're paying attention or not. Okay, I hope you're paying attention. Again, in some sense, it doesn't matter because you can go back and look at this at home, but yeah. Okay. It's kind of, I'm going to pretend that you are paying attention because otherwise why are you here? So I'm just going to, like, sort of mathematically, it makes sense to me that you would be paying attention. Right? If you weren't, why are you here? QED. But yeah. Okay, so now we get to kind of the climax of the course. Okay, this is the theorem of Ascoli-Arzela. Okay, so which in most texts is called the theorem of Arzela-Ascoli, but my professor always called it Ascoli-Arzela, and so I'm going to go with him. Yeah, although I rarely understood anything that he said. We even made up a song about how confusing he was. No, I didn't, but somebody did. Okay, so here we go. So here's the theorem. And this is basically the compactness theorem that we're looking for, right? That what guarantees the existence of a convergent subsequence, right? With respect to the sup norm metric, right? And remember, the sup norm metric, convergence with respect to the sup norm metric is uniform convergence. Okay, so we're wondering, what conditions give you sequential compactness with respect to the sup norm metric? In other words, guaranteeing uniform convergence. Okay. So here it is. You have a sequence of, again, complex value functions on some set K. If K is compact, if the functions are pointwise bounded, on K, and if we have equicontinuity, then the functions are in fact uniformly bounded on K. And 2, f sub n has a uniformly convergent subsequence. Okay, so this is one version of the theorem. There are others. There are others, roughly saying that if you have a subset in the space of continuous functions on some compact set, this thing is compact in the supremum metric. If and only if K is, let me call it F, sorry. F is uniformly bounded and equicontinuous. Okay, so that's another maybe more friendly looking form. Okay, but this is kind of a more general form of that. Anyway, they're along the same lines of result. Okay. Okay. So. Okay. So you see what this is giving you, right? It's saying that if you're on a compact set, you've got continuous functions on a you've got functions on a compact set. The functions are equicontinuous and pointwise bounded, right? Then you're guaranteed, this is the important part, then you're guaranteed a uniformly convergent subsequence. Okay. Okay, this part B is really the important part. Right? As you see, the other formulations of this theorem kind of hide the fact that pointwise boundedness is necessary to get uniform boundedness. They just assume uniform boundedness to begin with. So this is really the key here. This is really the point of this theorem. Okay. So let's prove it. Let's prove part A, right? We want to show that these guys are uniformly bounded. Right? These guys are uniformly bounded. Okay, and K is a compact set. Okay, and we're equicontinuous. And we're pointwise bounded. Okay, you guys can probably do this. Here is our usual compact set, right? We have equicontinuity. We're trying to show that right, so we have pointwise boundedness, so that at every point, right, the family is bounded above and below. At every point, the family is bounded above and below. But we want the family to be bounded on the whole set above and below. Right? We want a uniform bound, not just a bound at every point. Okay? Okay. Fortunately, we have equicontinuity, right? Equicontinuity says that our family doesn't vary. Our family kind of varies at a controlled rate, right? It's not like some guys can vary slowly and other guys can vary very wildly, arbitrarily wildly, right? Everybody's variance is kind of controlled. Okay. So fix an epsilon. Okay. You could take epsilon to be 1 if you feel okay. Okay. Then by equicontinuity, we know that there exists a delta that works, right, such that if the distance from x to y is less than delta, then the distance from fn x and to fn y is less than epsilon for all n. Right? That's the equicontinuity part. So there's a delta that works everywhere. Okay. Can you guess what we're going to do next? we're going to use the compactness. We're going to use the compactness. So what will we do? We want to get an open cover, right? Then we're going to finite subcover. Okay. So cover, oops, not cower, don't cower. Cover K with delta neighborhoods, right? Okay, right? Cover every single point with a delta neighborhood. Right? Every single point is to be covered with one of these delta neighborhoods, the delta from this epsilon here. Okay. Well then, by compactness, we know that there exists a finite subcover. N delta x of I from I equals 1 to n. I don't want to use n, p. Right? So we know that there's a finite subcover. There's some x1, x2, x3, through xp. So that their delta neighborhoods cover the set. Okay. Can anyone see what we're going to do next? We've got compactness, we've got pointwise bounded on K, we've got equicontinuity. Anyone imagine what we're going to do? So we know that over every neighborhood, we don't vary that much. Josh? Okay, that's all right. We know that over every neighborhood here, the values don't vary that, for each function, the values don't vary that much. Okay, they don't vary by more than 1, let's say. Okay. Kishan?
Do we find like a minimum and maximum of like x1, x2,
Yes, a minimum of what?
like the minimum value of f and x
Of f and.
of like x1 to x2.
So remember, these guys are just in some metric space. These are just points in some metric space. We don't know, they don't necessarily have an order on them. So it's not these guys that we're going to find a bigger or smaller. We want a bigger.
What kind of like the maximum of all the xi's?
Not
mf and xi's, right?
the opposite. You actually want to control the size of these guys,
Yeah.
right?
Maybe I did.
Okay, that's okay. So remember what we're trying to control. We're trying to control we're trying to get a bound on f on all values like this, right? We'd like to find something. We want some m such that this thing is smaller than m for all x in our K, for all n in our over our range. Okay, right. Okay, and so what we've done is we've created these neighborhoods over which every single fixed. If we look at a single, if we look at individual functions, they vary by less than 1 over those neighborhoods. Okay. So now we're going to use the pointwise boundedness. That's the only thing we haven't used yet. So we'll say, well, look, the f sub n is a pointwise bounded family, right? So that means that for each x of I, fn x of I is smaller than some n sub I for all n. right? So if we look at the centers of each of these disks, right? Look at the center of each disk. We've got a bound on all the functions at each of the centers. Okay. Further, we know that over each disk, each function doesn't vary by more than epsilon. Right? So what does that tell you? That tells you that on the whole disk, m sub I plus epsilon dominates all functions. Right? So we take then just the maximum of all the m sub i's and add epsilon to it, and that will dominate everybody everywhere. Okay, so that's the idea. So let m be the max of m1 to mn plus epsilon. Okay, then for any x in K, we know x must lie in some one of those finite neighborhoods, right? And so the value of f sub n at x is controlled by the distance of that to x sub I plus the value at x sub I. Right? But this is smaller than epsilon, and this is smaller than m. Okay, so, I'm sorry, this is smaller than max. Okay, so that's why this m works for everybody. Okay. Okay. So as usual with compactness arguments, you sort of think, what would happen if I had a single neighborhood, right? What would I have? How would I do this if I had a single neighborhood? Well, I know at the center of the neighborhood, I've got a bound for everybody at that point, and I also know that everybody doesn't vary very much on that neighborhood, right? So you're bounded by the variance plus that bound at the center, right? And then you just say, okay, well I've only got finitely many things, so I can do that over the whole space. Okay, so that's the first part, showing that these guys are uniformly bounded. Everybody, any questions about that? Okay, give me 1 second to remember what's going on here. Okay, so now let's do part B. Showing that we actually have a uniformly convergent subsequence. Okay. Okay. So part B, claim that this thing has a uniformly convergent subsequence. You say, well, look, our set is compact, right? so we know that that there exists a countable dense subset E sitting inside of K. Okay, so this was a homework problem from chapter 2, I think, or chapter 2. Okay, so we have our set K, and then we've got our we've got our countable dense subset inside. Okay. So now at this point we pull out the theorem that we did last time, which was that if you've got a countable set and you've got pointwise, if you've got a countable set, then you can create a pointwise convergent subsequence. Okay. So we know that by theorem 7.23, there exists a pointwise convergent subsequence on E. Okay. Okay. So we've got this pointwise convergent subsequence. Let's call it f sub n k, and it's on E. Okay. So remember, we're trying to find a uniformly convergent subsequence, and our claim is that, in fact, this pointwise convergent subsequence converges uniformly. On K. Okay, so that's this pointwise convergent subsequence that we derided last time actually is the uniformly convergent sequence that we desired. Okay. So the way you want to think about it is like this. If we were pointwise convergent on a finite collection of points, right? Suppose K were just a finite collection of points. Then you would have pointwise convergence on a finite collection of points, but that would be uniform convergence, right? Because given your epsilon, you could choose an n that works for each point, and then choose the maximum of those n's to get an n that worked for everybody, if you had a finite set. Okay, but we don't have a finite set. However, we do have a compact set. Okay, so what we do is, so let's think about it. So we want to show, remember, that for all epsilon greater than 0, there exists an n such that if k and l exceed n, then fn k x minus fn lx is smaller than epsilon. Okay. Well, so fix epsilon greater than 0. By equicontinuity, we know that there exists delta such that if points are within delta of each other, then fn k x minus fn k ky is smaller than epsilon over 3 for all k. Okay. Okay. So you'll see why how we use equicontinuity in a second. So at this point we'll use compactness. Cover K with n sub delta E, where E ranges over our dense subset. Okay. I cover every point in E with the delta neighborhood from equicontinuity, and that will cover the whole space because the E is dense in K. Then there exists a finite subcover, n delta ei, and I equals 1 to P. Okay. Okay. So now we've got these points E1 through EP, just a finite number of points here, whose delta neighborhoods cover the whole set. Right? So there's a finite number of guys, their neighborhoods cover the whole set. Okay. You see what's going to happen? This is our finite set, we've got pointwise convergence on each of the finite, each of these points. So we've got uniform convergence over the collection of points E1 through EP. And then we'll use that to get uniform convergence on the whole set by invoking equicontinuity. Okay. So here we go. We say, well, look, we know, since we've got pointwise, we have pointwise convergence at every point, including E1 through EP, that there exists an n such that k and l exceeding n implies that fnk ei minus fnl ei is smaller than epsilon over 3, right? For all I equals 1 to p. Right? We have uniform convergence on this finite set. What about a point that's not in the finite set? So for x in k, well, we know that x has to lie in one of the EI neighborhoods, in the delta neighborhoods of one of the EIs for some I, right? But then if k and l exceed n, we see that f sub n k of x minus f sub n l of x is controlled by, using the triangle inequality as usual, f sub n k minus f sub n k ei plus f sub n k ei minus f sub n l ei plus f sub n l ei minus f sub n l x, right? But this is smaller than epsilon over 3 because x lies in the delta neighborhood of EI. So by equicontinuity, this and this third term are controlled, and then this middle term is controlled because of because of the pointwise convergence on the finite on that set of centers. Okay, so this is also less than epsilon over 3, and so we get, as usual, that this is smaller than epsilon. Okay. So that's the proof of Ascoli-Arzela, and one of the great results in this course. Okay, so I'm gonna stop there.